All right, so let's just start off with example 1 from the MATLAB examples, and I will sort of talk you through this. And if you want to see something different, or you don't understand something, or you want to see something related, just feel free to ask. So this first example, I guess these examples were designed both to demonstrate MATLAB stuff and as well as to kind of show you how I made the figures that you saw in the last couple lectures. So I mean, the very first figure I think was just something very basic like a histogram and some summary statistics. So this first example is pretty straightforward. I think maybe I'll just copy and paste for things so it takes less time. So I like to generate fake data, and that's why I like random so much. So here we just generate a set of data. So this is just 100 random numbers, and I have some weird operations just to make it a little more interesting. So I sampled 100 numbers from the normal distribution, square them just to make it non-normal immediately. So that's just this dot operation. Remember, it says element-wise exponentiation. And then I'll just scale it by some number just to give it some just to make numbers bigger, and then add offset. So I just immediately generate some random data, 100 numbers that we can start to demonstrate some ideas on. So we have these numbers, and the first thing I would do is, if I was just exploring some data set, is do a histogram. So that immediately gives me some notion of how big are the numbers and how they're distributed. And so I know the range now, they're between 20 and 70, and I probably chose too many bins. This 100 means bin up the range of the data into 100 bins. Let's just do 30 bins now. Okay, it looks a little better. I know something about the central tendency. It's probably 25 or 30, so that's good. All right, we have X. So in the example, I just computed some very basic statistics, right? So go ahead and use mean. Mean is a built-in MATLAB function. Pass it the vector. It assigns it to this variable mn. And the mean is 27, which made sense based on what we had seen. And then likewise for standard deviation, we can easily use the built-in function for that. Check it out. It's almost 10. So that makes sense. And then, so mean and standard deviation are these sort of very simple and parametric summaries. We can also use percentile. I think we went over this function to generate some percentiles. And so the 50th percentile, remember, is the median. So that's why it's included here. There's also 2 other percentiles I asked for. The 16th and the 84, just because that corresponds to it's 34% below 50 and then 34% above 50, and that gives you the central 68%, which is analogous to plus or minus 1 standard deviation of a Gaussian. So I can use that function to calculate those percentiles of X, and I can inspect that, and that's fine. So far pretty straightforward. And then the rest of this is just visualizing these, because visualization is useful. I had already done the histogram command earlier, so that shows you the distribution of the data, and then it's useful to also visualize some summary numbers on the figure, so we have to use some figure plotting to do that. So first I'm going to use the axis command to determine. So the figure already has some axes, and MATLAB automatically scales the axes in an intelligent way to sort of cover the data. So it put the x bound, or the x-axis, from 20 to 70, and the y is from 0 to 40. And we can use the axis command to obtain that information. So I just put that in the variable ax, and first 2 numbers are the x bounds, and the second 2 numbers are the y bounds. So the reason I did that is I want to plot some things that will rely on that. So I just want to plot a vertical line at the mean. So the vertical line, I mean, you got to do this from scratch. So in MATLAB, you use the plot command. You need to know what are the x coordinates and what are the y coordinates. Well, we're going to use the x coordinate at the mean, so we already know that, mn. But we need to know the y coordinates, and that will depend on the figure that was already existing here, right? So that's why I needed this information, 0, 40. So once I know that, then I can issue the plot command. The 2 x coordinates again, it's a line where the 2 points have the same x coordinate, the mean, and the second argument are the 2 y coordinates, and that is just 0 is the first one, and then 40 is the second one. And that's fine. And I'll make a red line and give it a line width. So a line width is a property. I don't think we really went over this. So let me just show you the output of that. So it just plots a red line defined by 2 points. I assign remember there's a figure handle or a plot handle that refers to that element we just created. So h1 is this. It's just an identifier essentially. And that actually helps me segue to why I was trying to explain something about the line width. So this is just a pairing of attributes that MATLAB uses to control figure plotting. So let me show you. So h1 refers to that red line. So I can do something like get h1. So get is a special function, but essentially get tells you certain properties associated with the h1 object. And so there are a bunch of them. And line width should be one of them. So that's right here. So this is telling me line width is 2, and that's because I told it to be 2 already in the plot command. But certain commands can't accept these types of attributes in it. So what you can do is first make the thing, in this case a line, and then after that you can do something like set some property. So let's just change the line width to 10. So h1 again is the thing I assigned, and then we can issue that command, and now it's a big fat line. And as you can see, there are many other attributes that you can control. I guess to understand what each of them is, you can look in the MATLAB documentation. Some of them are pretty straightforward. Line style, that's pretty straightforward. Currently it's just a single hyphen, meaning a solid line, but you can make a dashed line just like that. So if we can look at that, there you go. So anyway, so that's just a line showing where the mean is. It's useful to have a visual representation. We can also plot some other lines showing plus or minus 1 standard deviation. That's this line and that line. And we can also look at the percentiles. So here, maybe I should make my font bigger, like so. All right, so for the percentiles, I have a slightly different...
So can I ask a question?
Sure, question.
Why is there 2 MNs and 2 MN minus SDs?
Oh, sorry. So in this call, we want a line that's 1 standard deviation below the mean. So that would be this line here. Right. And to draw that line, we need to know the 2 points that make the line. And so both of these points share the same x-coordinate. And so the x-coordinate is MN minus SD, which is a scalar minus the scalar. And then we got to repeat that because we need to specify the x-coordinates of both points. Right? So the x-coordinate's the same, it's just the y-coordinates that's different. And the y-coordinates is accessed through this variable ax, and specifically the third and fourth elements of that vector. And then we got to do something very similar for the other line that's above the mean. And notice I create a figure, I save the figure.
Sorry, access the built-in command, and it tells you the bottom, the top of the plot.
It tells you the x range and y range, as you see right here. So, and you can also use axis in other fashions, and maybe that's a little confusing. You can do something like axis off, and that's just a command that does that, which is kind of unrelated to the fact that you can also call axis like that, which gives you the bound. So a little confusing, but that's life. So notice I saved the figure handles. I don't think I really use it, but it's just good practice in case you do want to use it in the future. For the percentiles, a little programming hackery. So in theory, I can make H4 and H5 and H6, but as you get more comfortable programming, you'll realize that that's a bad idea. So here I'll just make a vector of figure handles. And so I'm just going to initialize H4 to an empty vector. And then I'm going to loop over each of my percentiles. Remember, percentile is just a vector of 3 numbers. I'm just going to loop over that, and then each time I'm doing exactly the same thing. I'm going to repeat the x-coordinate, give the y-coordinates, and issue the plot command and save the figure handle. So if I execute that, then we check out H4. Notice I have 3 figure handles now, or object handles rather. And the fact that H4 is a vector versus having to make a H4 variable and an H5 variable just means that, it'll make your code more readable and more compact and easier to manage. So let's just look at the effect of that. So now we have three green lines. Sorry, my axis is gone. I think I should do axis on. Okay, that's better. And okay, so that's fine. So now we can see percentiles, which are much more reasonable for these weirdly distributed data, whereas the parametric, mean and standard deviation are kind of not that descriptive for these data. What else can we do? Let's put a legend. So the legend, I made dotted lines and so forth. So actually, let me go back to what the example does. So let me just reevaluate all of this down like that. Okay, so now, the way I've designed the figure, I have two things, a red line and green lines. Actually, there's multiple instances of each, but at least that's the way I designed it. So here I just have to give legend two plot handles. So h1 is just the first one I did for the red lines, and then just give it the first plot element defined in h4, and then I'll just label that with some strings here.
In the h4 handle, you have percentiles p and 1 and 2.
Oh, sorry, I didn't explain this little mat. So yeah, so remember we need to repeat the x-coordinate.
Yeah.
And so I could do something like, I could do it the dumb way, which is just p tiles, which is fine. Or I could just do repmat. Repmat repeats this scalar according to this specification. Right? Do you remember? So, you could do repmat 110 and it'll. And so obviously this is a lot cleaner than typing p tiles p 10 times, right? So, but if it's only 2 times, then it's a trade-off. Maybe you just want to do that, which is fine. All right, so we can make a legend, which I think we did. There you go. And the last bit is make a no title, label the axes. Okay. So statistically speaking, what have we done? We've plotted a simple histogram of the data that's shown in blue, and then put little lines just to indicate some summary numbers that we might want to use, the mean or the 50th percentile, i.e. the median, and so forth. Simple example. So without further ado, let's keep going, because doing the exercises yourself I think will be more informative, but at least let me talk you through the next couple. All right, so the next example, statistically, the concept, what we're describing is important, basically being able to run simulations for yourself to sort of check your code or check your ideas, and so that's very useful. And so we're going to run some Monte Carlo simulations, which just means we're making use of random variables, essentially, randomly generated data, and we're going to look at the concept of correlation. So really all we're doing here is seeing what kinds of correlation values you can expect to obtain by chance, and we're going to control these simulations using some constants here. And of course, to make it a more interesting simulation, we can modify this to sort of try different values for these little parameters and see what happens in our simulations. So good code is flexible, and so that's why I define these up front. Like, this is the only spot that I'll define number of simulations to run and number of data points in our sample. So instead of doing a search and replace in some code where their hard code is, better just to define it up at the top, so you only have to change one spot. So we're going to run 10,000 simulations, and we're going to run a simulation where we draw only 50 data points from, let me clear the screen here. All right, we're gonna, 50 data points. So intuitively, we want to simulate drawing 50 random numbers from the normal distribution, and we're gonna draw 2 sets. So it's like there's 2 quantities where we have 50 subjects and we're measuring 2 quantities from them, and we're looking at correlations between those quantities. And in our simulation, there is no intrinsic correlation. It's just because both are getting sampled randomly from the normal distribution. So the true correlation, in the underlying population is 0. It's just with only 50 samples, we may by chance get 0.1 or 0.2 correlation, and that's sort of what we're trying to get at here. So to do that, we're just going to loop over simulations. Actually, there's much more efficient ways to do this in kind of a vectorized fashion that can just do it all in once, but for sake of example, we will do a for loop. And it's fine given that we're not pressed for computational time. So good practice is to allocate your results. So we want to store something like a collection of randomly obtained correlation values, and we're going to collect that in this variable, and we want to pre-allocate this. It's just good practice. Alternatively, you could do something like pre-allocate to the empty matrix, which is fine, except that when you assign values to an empty matrix, MATLAB has to increase the size of it, and that's kind of, there's overhead involved. It takes longer. And so if you know the size of the matrix you want anyway, it's useful from a sort of speed perspective, and it's also useful from a code reading perspective, because then if you're reading the code, you or someone else reading the code, they already know what dimensions this will be, like, and that's just useful. So this will just be a vector of 10,000 numbers, and we're going to initialize it with zeros. Zeros is just sort of the default. It creates a matrix of all zeros. Of course, that's not meaningful, but we're going to populate it with values in this for loop. So pre-allocate the results matrix, and then we're just going to loop over 10,000 simulations. So that's a for loop. And in each for loop, we're just going to draw from the normal distribution 50 data points. That's controlled by this variable here, and 2 sets of them, because we have 2 hypothetical quantities that we're taking measurements of. So I'm just going to do the first iteration. So when num is 1, I'm sort of acting as if I'm the for loop. Num is 1, and then we're going to issue this command. So data now is a 50 by 2 matrix of completely random numbers drawn from the normal distribution. So Gaussian distribution, mean 0, standard deviation 1. We could look at it. It's not very meaningful, but okay. That's fine. And next step, and that's it, which is correlate those 2 columns of numbers. So core is a built-in MATLAB function and takes 2 column vectors, and if we issue that command by itself, we can just see what it does. It tells us what the Pearson's correlation is. But we want to save that into an output, so we want to assign that. So we're going to say the first element of results, it's just a vector, will be assigned that value. That's fine, and then we can check out, well, if I check out results, if I hit enter, you're going to see 10,000 numbers. That's not useful. So let's just look at the first 10. Okay, everything was 0 except for the one we just assigned. So our for loop seems to be working. Great, so let's just call the whole for loop. And my laptop is kind of slow, but it should be done very soon. Okay, it's done. So now we could check out the first 10 elements of results just to make sure, okay, there seem to be values there, things seem to work. So we're happy. And then the last bit, there's not much going on. We're just going to visualize the results. So histogram, again, first thing I would like to do. Looks pretty reasonable. It's centered around 0, but we have some spread as expected. Let me close this other one. And there are a couple other things I just did just to make the figure a little more useful. We know that it should be symmetric, but for whatever reason, MATLAB automatically determines the axis range based on the data you give it, and it's not symmetric. Let's just make it symmetric to be a little nicer looking. So again, I have this axis call to figure out what the current axes bounds are. So we're concerned about the x-axis, negative 0.8 to 0.6. That's not symmetric. So let's quickly take the larger of the 2 numbers. So we take the absolute value, just so that negative 0.8 becomes 0.8, and then just take the max. So this says absolute value of a 2-element vector, that's fine, and then take the max of that vector. So what's the maximum x deviation in some sense, and it's 0.8. So now I'll just use 0.8 and rescale my axes. And so now we can use axis as a function call where we say, aha, I want an x range that's symmetric, negative max, which is 0.8, to max, and then preserve the y range because we don't, because we trust MATLAB that it shows a reasonable y range. So now the graph is symmetric, which is nice looking, and then just put on some x label and y labels. So this shows us randomly obtained correlation values, how they're distributed. Shows us that we can expect on average the correlations are 0, but there's some spread. And then the rest of this example just sort of puts a number on that spread. So let's say we want some sort of bounds on our correlation. So let's just take the central 95% of this distribution. What is that number based on our simulations? And so here we take the absolute value because we presume that things are symmetric. So we'll just say negatives and positives are the same for the purposes of this bounds determination. And then we take the absolute value and just take the 95th percentile of that. So that says 95% of my data points are below this magnitude. And I say magnitude because magnitude implies positive and negative are treated equally. So 0.28. That by eye looks reasonable, and then to prove it, not really prove it, but to visualize it, we can put little lines. So this is very similar to what we had just seen. We're going to put some lines at that value, which was empirically determined. So that's plus or minus 0.2821. So you can eyeball. Does it look like 95% of the mass is within those bounds? It looks pretty good. And then we can put a legend. That's fine. Like that. And then we can put a title even. So here, remember sprintf is a string constructor command. So we give it a string, and we're going to shove in this one scalar with this sort of formatting string. So this says something like 4 decimal points with a floating point representation. So you construct the string, and then you give it the title. And so title just puts up that string up there. So all we've done is run a simple Monte Carlo simulation, and we've learned something about the kinds of correlation values you might get if you have 50 random samples from bivariate normal distribution.
Why is this called Monte Carlo simulation? Is there any
Monte Carlo refers to a city, I think, where there's a lot of gambling. Gambling involves chance. Wikipedia could probably tell you. It sounds nicer than what? Random simulation? Monte Carlo simulation? Random simulation? I don't know. Okay, so moving on. Don't want to spend too long on this first part. The next two examples, I think, are just bootstrapping and randomization. So really, these are just resampling techniques, which is not much. It's easier to implement in MATLAB. And I guess there's a little statistical baggage around that. So first step for this example, generate some data. So actually, I'll tell you how did I make this? Well, I did it something like this. So let's just generate some random data as usual. So ran instead of ran-n will generate from the uniform distribution. I forget what I used, but let's just see that. So this just generates 50 random numbers sampled from the uniform distribution between 0 and 1. So notice all the numbers are positive, as you can just see. Actually here, I'll just do a quick example. Let's generate 1,000 from the uniform distribution, do a quick histogram. Too many bins. Let's do 10,000. 10,000 numbers, now the 100 bins is good. So you can see they're all between 0 and 1. And it's roughly flat. There's some random variability in the histogram. Anyway, so to generate my fake data, I would just do something like that. But then you kind of want something you can paste in a text document. So then I can just use a built-in MATLAB command, mat to string. And then there's too many digits, so then mat to string, comma 2. Then you get some fake data that you can copy and paste. Anyway, so the purpose of this example is to just demonstrate in a very basic fashion what bootstrapping does, or how you would do bootstrapping. And specifically, we're going to try to get error bars or confidence intervals on some correlation. So again, we're dealing with correlation. So we have some x is a vector, y is a vector. These are quantities that are probably correlated, hopefully. Let's just do a quick scatter plot to check that out. There you go. So you can kind of see red dots, and there's some positive correlation. It's pretty weak. Fine. So those are our data, and we can compute the correlation between the two. I think that's probably the next step. I should just copy and paste, yeah. So Control C to stop that command. So we can run core. Remember, this is just a quick shortcut for making a column vector. I think core requires column vectors, so we're just going to say colon. I forget exactly what. Anyway, so we called core and 2 column vectors, and we can look at what is the value of this variable. Oh, so the correlation was pretty high.
Sorry, if you didn't put the column there, even though it's a 1 by 50, would it still not?
I'm pretty sure, unfortunately, it fails because it expects column vectors, I think. So that's why. Anyway, so the correlation between these 2 variables is 0.56. Now we want something like a confidence interval, like how trustworthy is that correlation value. So we're going to use bootstrapping. So very, very simple. It's just a quick for loop, 2 lines within the for loop. As usual, we pre-allocate. We're going to run 10,000 bootstraps. So we're going to save 10,000 numbers. Each number is just a result of 1 bootstrap. And we're just going to do a for loop over that. So let me quickly pre-allocate, show you the first for loop. So the first time around, num is equal to 1. So then we can issue these commands in between. So the first step, and this is really the only step of bootstrapping, it's 1 line in MATLAB, is we just have to construct a vector that does the bootstrap sampling for us. And in MATLAB, this is done through indexing. So you have a matrix, and you just say, I want the first and fifth and second and whatever elements. And so this is really just a lot of legwork just to do something quite simple, which is give me random numbers between 1 and the number of data points there are. So there's actually 2 quantities, right? X and Y, and there's 50 of each. So we want to draw a bootstrap sample from these 50 data points, and that means we need to randomly select with replacement 50 of these numbers. And so one bootstrap indexing vector might be something like, first I choose 17, then I choose 10, then I choose 1, then I choose 9, and then maybe I choose 10 again, and then choose 20, and so forth. And there'll be 50 of these. And these just are one indexed, right? These are just positive integers referring to the elements of whatever we're going to index into. So how do we generate a thing like that? I think maybe MATLAB might have something like randint range or something, but that's fine if you want to use a built-in command or write your own or do it on the fly yourself. That's what I did here. So pick length x. So this, again, remember that we're writing general code. So maybe next time we run this, we want to use more than 50 data points. So I don't want to type 50 in here. That would make your code not general. So instead, I'll just get the number of data points on the fly using length. So this says, give me 50 random numbers between 0 and 1. And then we'll just multiply those by 50 and then round up. And that's just sort of a way to get numbers, integers between 1 and 50. So that's all that's happening here. And we can just check it. So issue the command, check it. So now, as you can see, they're random looking and they're all integers and everything's fine. Okay, so that's step 1 of 2, and then step 2 is use it. And then you're done. And how do we use it? We just use that to pull out data points from the data points we have. So x and y, remember, is what we have, and just index into x. So this just says pull out these specific elements of x. Notice there's a repeat here. There can be repeats, so 2 occurs twice. And we're just going to pull out those data points from x, pull out those data points from y, and then compute the correlation. And then save that to our little vector. Transpose, right? We need column vectors. It's annoying, huh? You could write your own correlation function that works with row or column vectors, and then you can save 2 characters. All right, so that's pretty straightforward. Let MATLAB churn away. Oh, and also, I put in comments here just in case. So MATLAB has a Bootstrap function which kind of does this step for you, and also allows you to do some more complicated things, like you can have more than 2 arguments. But you could look at it and sort of figure it out, and I put the command here if you want to figure it out. But, you know, it may be more complicated to use that versus just code it yourself. So you decide. anyway, so it's done. Now what we can do, I didn't do that in an example because we know how to do histograms, but it's useful right now to visualize what happened. So here's a histogram of all the Bootstrap results. We see the distribution, it's unimodal, makes sense. It's peaked around the value that we saw based on the actual data, which was 0.56. Correlations are bounded at 1, right? That's why there's no values above 1, makes sense. We ran a lot of simulations. The histogram looks very nice. We could actually bin it a little more finely. There you go. And this shows, I mean, this is quite a wide range. This says that often we might, based on, remember, so let's talk about statistically what we did. We said our 50 data points are, let's take it to be representative of the true population. And then we simulated random samples from that population. We drew 50 random points, computed correlation, did that again and again and again. And this shows that there's a lot of variability based on the fact that we only have 50 samples. You can easily get a correlation value of, say, 0.75, which you may be happy about, or you can easily get a correlation of 0.3, which maybe you're not happy about. So I think the rest of the example just puts little numbers on that. So, okay, suppose you want 95% confidence interval, so we need to get the percentiles of the central 95%. So that's like that. And then we can, oh, I guess I don't put the histogram. Anyway, so these are the values. 0.32 is about here. 0.75 is about here. So that makes sense given the histogram. So that's a pretty wide range. And I guess in the example, I just report it on the scatter plots. Oh, okay, so we do a scatter plot of x versus y using red circles. That's this argument here. And then just label the axes and then put the title with the relevant information. So I report what is the actual observed correlation and then what is the 95 confidence interval we've obtained here using a Bootstrap approach. And that's done like this. So here I just have one format code for the lower bound and then another format code for the upper bound, and then we got to separate that out in the sprintf call. So we just give the first p tiles and the second p tiles. Anyway, so we'll just do that. So looks like that, makes sense. We see the data, axes are labeled, we have the title bar, and we're happy. Or sad if you wanted a tighter confidence interval. Any questions, or I'll just move on to the last example and then we can get to the exercises. So randomization, I mean, this looks almost identical. We're just playing with how we resample the data and how we interpret what we're doing. Clear the figure here, get our fake data. We have x and y, let's just check the dimensionality. Oh, 20 numbers now. And what are we trying to do with these data? Well, we look at the data and whoops, I gotta close all my figures, okay. So these data, I can't really tell, maybe a negative correlation? There's not a lot of data points and it's a weak effect. Just do a quick correlation between the two. Okay, negative 0.2, pretty weak. You might be interested in putting a p-value on that. That is, remember, testing the null hypothesis that there actually is no relationship between these two variables. Oh, so that's the first, so save the actual correlation out. We're proposing this null hypothesis and we're going to see if we can reject it. So we're going to do that in this little randomization method to do that. So the logic is, if the null hypothesis is true that x and y have no real relationship, then we could just shuffle the x, basically assign new x coordinates to break the relationship between the x and y vectors. Currently, x and y have a certain relationship, that's what we saw. But under the null, there is no relationship, so we should be able to randomize the x values and get equivalent data. So that's the logic, and we're just going to do that in a for loop. We're going to do 10,000 randomizations, initialize, and then within the for loop, very, very similar. We just create, I mean, the key line is this line, and so let's just look at what that does. So that line just makes, randperm is a built-in function. Given a integer, it just gives you a random permutations of the integers up to that, positive integers. So if we call that, we need length x, so up 20, we need an index vector that's 1 through 20. So this is just a random permutation. So this will shuffle. So here there is no replacement. We're just reordering the x values randomly. And we're going to get the index variable and then use that indexing vector to shuffle up x. And then we can compute a correlation against y. So why should we not do this? Because it's the exact same ordering, and we haven't broken any relationship between x and y. We've just sort of reordered each of the pairs, but that's not going to affect the correlation, right? So you definitely don't want to do that. You could generate 2 completely random indexing variables if you wanted and did that, but that's extra computational time for no actual benefit. If one's random, then you don't need to, it's not doubly random if you do it twice. All right, so do that, and then we're almost done. Okay, so we're going to look at let's do histogram, our favorite command. So this histogram shows you the results of all these randomizations, 10,000 values, and as expected, they're kind of centered at 0, and there's some spread showing you that if the null hypothesis is true, you can expect that you can obtain any of these types of correlation values. And in some sense, it's bad that it's so wide. This is saying that if there was no relationship between x and y, you can actually get easily a 0.4 correlation just by chance, just by the sampling process.
If you increase the number of randomizations, how will that change?
So in theory, the number of randomizations just affects how noisy looking your distribution is. So here, let me do an example. Let's only do 100. As you might imagine, our histogram will not look very... So here, hopefully what I've done... Okay, the only difference between these two, notice I forced both to have 100 bins, so they're roughly the same bin size. Obviously, this is a very noisy looking histogram, but presumably you're sampling from some underlying thing that's constant across the two cases. It's just here we only have 100 samples, and here we have 10,000. So yeah, bigger is always better, and that's all. I guess, I mean, if you really want to, so the only reason not to go bigger is if there's computational time. And so if you have a scenario that you're pressed for that, then maybe you would want to do something like explore the dependence of something on the number of simulations. And that something is probably something like a percentile or p-value or something. So for example, if you only have 100 simulations, you can, see what you get on one set of 100 simulations in terms of a p-value or a confidence interval or something, and then run that simulation again to see if that fluctuates a lot. With a lot of simulations, your number that you care about, the p-value or confidence interval, will be stable. So, whoops. Let's go back to the 10,000 version. The only last bit is, we already did it. So we looked at a histogram, close that. Whoops. And then if you want to put one number on this entire distribution, that's the p-value. So let's see. So here we can, so remember the actual correlation is the one we actually observed before all this randomization bit. So we can put a straight line at that value, which was negative 0.2. It's not really that far in the tails, so it's not very extreme. And we can compute an empirical p-value here by basically counting what's the proportion of examples that are more extreme than what we observed. And so we can do that in a two-tailed sense. So we'll count anything that's more extreme than negative 0.2 and anything that's more extreme than 0.2 on the positive side. So that's this line here. So we're just going to do a quick logical comparison. So take the absolute value of our results, so that's in blue. So we're disregarding sign. And we're going to do a comparison of 10,000 numbers, that's what's in here, against one number. So this is just the absolute value of that scalar we have, so 0.2. So this is going to result in a logical vector. It's just going to be a vector of 1 when it's true and 0 when it's not true. And then we're going to sum all of those. So whenever it's true, I'm going to increment, and I'm just going to convert the 1s and 0s into one number. It might be like 6,000 of the, actually let's just do it. What is it? Okay, 3901. So that tells us of the 10,000 simulations we performed, 3,901 was more extreme than our observed correlation. And then we want to convert that into a fraction. So just divide by 10,000. So notice here I didn't subscribe to my philosophy of you should hard code. You know, this could have been something like number of randomization. And then you could use that variable here and here and here. You know, it's going to be up to you, you know, as you write code. Like sometimes it's quick and dirty to just put in the number, or sometimes you might want to take the time to, you know, define a general variable and so forth. But it's up to you how you approach that. Anyway, so if you divide by 10,000, then you get a fraction. Then you get, well, nicely, because we ran 10,000, it's just that number with the decimal over there. And then finally, just put that in the title. Nothing big going on. So we report the correlation, and then we can get a p-value based on our randomization tests. Okay, so that was a fly-through, hopefully fast enough, of what I have in the examples, and it runs, and so I just use the MATLAB publish command, as you know, since you did it for your homework, just to generate this little PDF that shows, you know, the code prettified in colors and so forth, as well as the output, just to prove that it works. So I find it a pretty useful way to show code and results. So